All right, general chemistry, hope you're doing well this week and you're getting used to this online learning environment. I'm going to give you a little bit of background for what you need to know this week for a new topic. This week we're going to cover new material on acids and bases. So today our goal is to define what is an acid, what is a base, and then you're going to do a little simulation with that this week. So first I want to just show you, you've seen these before for our demos. This is a really strong solution or high concentration solution of acetic acid. And how would I know that it's acetic acid? Well, I could read the label. It says acetic acid on it. But before they label it, how do they know that it's acetic acid? How do they know they produce acetic acid? And when we're using all these different acids back in lab, what makes it an acid and what makes the things that we use as bases a base? That's what we're going to be looking at today, the definition of an acid and a base. If you've gotten to school in a car that has a battery in it, or anywhere else, we're not going to school right now, I guess, but anytime you have a device that uses a battery, you have an acid in that. For car batteries, we have a lead sulfuric acid solution. If you've ever taken ibuprofen, or not ibuprofen, aspirin, you have taken an acid, and the compound's right there on your screen. What makes this an acid? What part of this chemical structure makes an acid? That's what we're going to look at today. Okay. Properties of an acid. I would jot these down. Acids are generally sour. If you've had sour candy before, it's because they've added an acid to it, and that's what tells your tongue that's a sour taste. They're corrosive. They can react with many substances to corrode them. What does that mean that they're corrosive? I want to give you an example of that. You might remember this demonstration in class. Hydrochloric acid, HCl, aqueous, dissolved in water. If you add that to magnesium, a metal, it fizzes, it bubbles, and the magnesium actually turns into, it's a single displacement reaction, that turns into magnesium chloride, MgCl2, and H2 gas. Well, when it reacts, the magnesium, it corrodes the magnesium. That's one of our ways of saying corrosion. It's just converting it to a different substance. So the magnesium still is there, but it's not in metallic form anymore, and that's what it means to corrode something. If you add this to your car, acids help metals rust really quickly for some metals, and some metals it helps them actually decompose and turn into a different compound. If you've ever seen like a marble statue or a limestone statue, acid rain helps that corrode. It doesn't just erode it like water would running down a rock. It actually corrodes it. It helps a chemical reaction occur to break it down over time. So that's what it means to be corrosive. pH is less than 7 for acids. Here's 2 acids that are commonly found at the grocery store. Vitamin C, your body needs this. It's called ascorbic acid. If you've ever had a chewable vitamin C tablet, it tastes sour. They add other things too as well. But vinegar, acetic acid, that's what this is. This is acetic acid. A lot of salad dressings have acetic acid. You wouldn't want to put this on your salad dressing because it's very high concentration of acetic acid. But the stuff that you do put on your salad, like Italian dressing, is just an acid. So they're all over. We use them all the time, and you see them all the time. Bases, properties of bases, they taste bitter. If you ever had to lick a bar of soap because you said something wrong growing up, maybe that was a couple generations ago now, but you would taste that bitter taste. Soaps are bases. They're slippery to the touch. If you get soap on your fingers and you run your fingers back and forth, you can feel it slippery. And acid doesn't have that property. Another term for base is alkaline. If you see this term, it just means basic as well. And bases have a pH greater than 7. Antacid tablets that you chew up, or Drano, you might have that in your house. Those are both bases as well. A quick review for naming acids and bases. We did this last semester, but I just want to review it because you're going to be seeing all sorts of different types of acids and bases in this unit, and you have to know how the names work. You could always Google it, but here's your quick review. If you have an acid with a polyatomic ion, so those would be compounds with a hydrogen attached to a polyatomic ion. In this case, we're attached to carbonate. This is how you name it. Name your oxo ion. That's your polyatomic ion. So in this case, we're carbonate. And then you take the ending of your carbonate ion. If it ends in 8, you change it to ic. And the way to remember that, if you remember it, I give you this little phrase. If you ate an acid, it would be icky. So 8 changes to ic. And ite, if our polyatomic ion changes to ite, or has the ending ite, we change it to OUS. So in this case, we're 8, we're going to change it to ic. It becomes carbonic, and then we add acid after it, and we have it named carbonic acid. So here's a list of our polyatomic ions. Our first one, carbonate, turn to carbonic acid. There's 2 protons attached to it because we have a -2 charge, and the proton's H plus with a positive charge. We want to make this neutral, so we need 2 protons here. We'll do one other example. Nitrite, that has a -1 charge, so we only need 1 proton attached to it to make it neutral. But the ite ending changes to OUS, and this acid would be nitrous acid. You can see the whole list of examples here. You can always Google it, but just a quick refresher for naming acids because we're going to run into them frequently. If you have an acid that is just attached to a single element, a nonmetal, so this would be things like chlorine or bromine or iodine or halogens if we're attached to those guys, or sulfur, this is how you name it. You put the hydro in front of it. And so 2 examples for that, HBr, we would take hydrogen bromide and we're going to change this into hydrobromic, that's our bromine, and we add the ic for all of these. These are all ic acids. So this is hydrobromic acid. We have hydrofluoric acid. We just saw hydrochloric acid reacting with magnesium. So these are your other types of acids, ones that are protons attached to only one other element. Okay. What is the definition of an acid base? This is our new material for this unit this week. And these 2 definitions here, people were trying to do chemistry a long time ago. Lavoisier was one of the first guys to do chemical reactions. He actually did some of his experiments with guinea pigs, but he was very interested in what happened to oxygen in chemical reactions. And oxygen actually in Greek means acid former. And it is essential in many acids. If you look back at the polyatomic ions list, many of those have oxygen in them. And he said that it's required for all acids. But a guy with the name of Davy, a little bit later, about 30 years later, discovered HCl and figured out that HCl has properties that are acidic in nature, and it didn't have oxygen attached to it. So he said oxygen's not essential to acid. So if we don't have to have oxygen, and this is not a good definition for an acid, that oxygen's involved, what is a good definition? Well, this is in 1808. In 1880, a guy named Arrhenius came up with a definition for acids, and it worked pretty well for quite a while. So this is your definition you want to write down. Acid is any compound that produces H plus ions. That's a proton. We're going to use those terms synonymously, proton, in solution. So I put an acid in solution. If it makes H pluses, it is an acid. If it doesn't make H pluses, it's not an acid. And so if I go back to this example here, floating around inside of here, there are a lot of H plus ions. There actually aren't H plus ions. We'll talk about what actually they turn into. They turn into this here later. But this produces, in Arrhenius' definition, this would be an acid because it produces those H plus ions. So let's go to HCl, hydrochloric acid. If you put this in water, hydrochloric acid can break up into the H plus proton and the chlorine. And what does that mean? It means if you're going to have an acid with this definition, you must have a proton in it. If you don't have a proton in it, you can't have an acid for the Arrhenius definition. And if you do have a proton, it's possible that proton can donate and it makes an acidic solution. So you will see it written like this, but you also see it written like this. HCl in solution. Solution means that we have H2O. We dissolve in H2O. It's going to produce H3O plus and not our H plus here. What's the difference between these two? Well, this is a common ion. You're going to see a lot in this unit. I would write down the name of this. This is the hydronium ion, H3O plus. So it does have a name for it. And here's what it means. What actually happens in solution, if you have HCl, our HCl is going to have this available proton here, and here it is in our reaction here. This would just be H plus. And if H plus is available to react with water, it doesn't float around by itself. It actually gets attracted by the extra electrons here. If you remember the Lewis structure for H2O, the oxygen has 2 lone pair electrons. Well, this is a really negative area. And that H plus comes along and attaches to that negative area. It's more stable being attached to the H2O than it is to be floating around by itself. And so what we find in solution, if you actually look in solution, you only find these. You don't find H pluses floating around in solution. You only find hydronium, your H3O plus. And what does that mean? It basically means, if you go back to this definition, if you see H3O plus, it's matching our definition. Or if you see H plus, it's matching our definition. And chemists will use both of these representations, either one of these, for the acid. They're lazy, so sometimes they don't want to write the H2O, and they'll write it like this. But what actually happens is the H2O takes that proton, attaches it, and makes H3O plus, hydronium. So there's your Arrhenius definition. If it produces H plus, it's an Arrhenius acid. I want to give you another example of that. So this is acetic acid. This is what I have in that little container that I keep showing you. And acetic acid has protons available in it. Here's a couple of them, but this is the one, it only donates one because of its structure. But it donates this one proton to H2O plus, or H2O, and it makes H3O plus, so that makes this an acid. I put this in water, and we get H3O plus, and that's what's happening in our solution. For bases, Arrhenius said if it's not an acid, and we want the counter of the base, it's something that produces hydroxide ions in solution. And a good example of that would be sodium hydroxide. If you put sodium hydroxide in water, it's going to break up. It's going to dissolve into ions Na plus and OH minus. The OH minus makes it a base. Calcium hydroxide has two hydroxides attached to it, and it also can dissolve in water and produce hydroxide, and that's what makes it a base. So the hydroxide ion is what you want to key in on here. If you have hydroxide in a compound and it can dissolve in water, then you have a basic compound. That definition lasted for a little while, so we're in 1884 here. And then Bronsted and Lowry, two other chemists, came up with a broader definition for acids and bases. And so this is your second definition. I would call this the Bronsted-Lowry definition of acids and bases. And it's pretty simple here. An acid is anything that donates a proton. How is that different than our Arrhenius definition? Well, Arrhenius said that it had to make H plus in solution. And here we're generalizing that and just saying that the acid has to donate a proton. It can donate any proton. It doesn't have to be an H2O. So in this case, the Bronsted-Lowry definition, H2O is not necessary for the acid. It could be a gas phase reaction where the proton's donated. The base, you'll see that there's no hydroxide here anymore. They're just going to call a base anything that accepts a proton. And our previous bases over here will still fall into that category. If you put a proton in the solution, the proton will actually attach to this and make H2O. So this chemical reaction, sodium hydroxide can accept a proton. The hydroxide will accept that proton. So this includes hydroxide solutions, but it also includes other compounds that don't have hydroxide attached to them. And I have an example here to show you that. So our HCl, let's look at that first. How is this an acid? Well, that proton attached to the chlorine goes to the H2O, so it donates that proton, making the H3O plus. That's what makes this an acid. And the H2O accepts that proton. That's what makes it a base. And when it accepts a proton, it turns into H3O plus. So this H2O is acting as a base, and we have an acid and a base on that side. In our second equation down here, if you just compare our left side of our equation to our right side of our equation, the NH3 accepts a proton from H2O to turn into NH4 plus. So how do we get NH4 plus? It steals a proton from the H2O. Well, that's accepting a proton. That makes NH3 a base. So we have a base here. The H2O in this case now is donating the proton. That makes it an acid. And we have an acid-base chemical reaction. Well, if you look at the other side of the equation, you can also think about this reaction going backwards. It could go back from the products to the reactant side. And if I go backwards, the NH3 needs to turn back, NH4 plus needs to turn back into NH3. For that to happen, it needs to donate a proton. And if it donates the proton, what accepts it is called a base, and what donates it is called an acid. So we have an acid and base on the product side, and we have an acid base on the reactant side. And you're always going to have that, an acid-base pair on both sides of the equation. We call these conjugate acid-base pairs. So in this case, NH3 and NH4, plus these two right here, they come from each other. The only difference between the two is one proton. We call these a conjugate acid-base pair. The base is the one that accepts the proton to turn into the acid. And then our H2O and our OH would also be a conjugate acid-base pair. The only difference between H2O and OH is one proton. And what's our acid here and what's our base? Well, in our equation, we just labeled this out. The H2O donates the proton to NH3. That makes H2O the acid. And the OH, as we go back through the chemical reaction in reverse, would steal the proton from our H+. That makes this the base. And so we have a conjugate acid-base pair, one acid and one base. And this term right here, conjugate, it just is a fancy term that means they go together. The only difference between these two compounds is a proton. And every chemical reaction for an acid-base reaction will have two conjugate acid-base pairs, NH3 and its conjugate acid, and H2O and its conjugate base. So just for practice here, see if you can pause the video here and solve for what the conjugate acid-base pair is for each of these three chemical reactions. So here's your answers. You want to look at that first chemical reaction, HSO4, and I want to find this compound on the product side, the right side. Well, where do I find that? The only difference between these two, it's right here, SO4. The only difference between these two is a proton. And so I want to ask, what happened to this compound to go to the product side? Well, this compound had to lose or donate this H+. It donates it to the cyanide. And that makes this an acid. It's donating a proton. Well, the cyanide accepted the proton to turn into HCN, so that makes this a base on this side. It's accepting the proton. And if we go to the other side of the chemical reaction, now we want to picture the reaction happening in the reverse direction, so happening to the left. How do I get SO4 and turn it back into HSO4? Well, it needs to take a proton. Where does it take the proton from? It takes it from cyanide. So the H will get donated, if we're going in reverse for this reaction, to the SO4. That makes this the acid, and the SO4 minus would be the base. And you're always going to find this, the two that differ only by one proton, it should be labeled as acid and base on either side of the reaction, and we have an acid base on either side of the reaction here. You'll always have one acid and one base on each side of the reaction. So for part A, here's your acid-base pairs, your HSO4 and your SO4, and your HCN and your HCN. Those are two acid-base pairs, and we have them labeled just like that. For B, your water gives up a proton to the hypochlorite ion. So this is donating the proton here. That makes H2O an acid, and its conjugate base would be right here. And then the HClO going in the reverse direction, this proton would be donated to the hydroxide. That makes this an acid, and this would be its conjugate base over here. It's accepting the proton, so this would be our conjugate acid-base pair, where the ClO minus was our base, and our HClO is our acid, and this would be our conjugate acid-base pair. H2O is the acid, and OH is the base. For our last one, if you look at this, this doesn't have a proton, so you can right away recognize, just like we did up here, this can't be an acid. It can't donate a proton, so this must be the base. And the H2O donates the proton to our S, so this is an acid. And then going backwards, if we go in reverse for this reaction, going from right to left, this would have to give the proton back. That makes this an acid if it's acting in the reverse direction, and this would be the base. And so there's our acid-base pairs, S2 minus and HS. Okay. Dissociation equations. For this unit, you're going to see them written a couple different ways, and I already showed you this once. Acids can be written with or without H2O. So you'll see HCl written like this, or you'll see an acid dissociated without the H2O. It's acceptable to write it either way. This is the most correct way to write it because this is what actually happens in the solution. But when you're writing a lot of acid-base reactions, a lot of times they'll disregard the H2O in it. For bases, if the compound contains hydroxide, you don't have to include the H2O. We saw that earlier. You can just dissociate it and say, here's what happens to my compound that has hydroxide. I break it into a metal and the hydroxide. And this is what I care about. This is what's defining it as a base under the Arrhenius definition. But if it doesn't have hydroxide, for NH3 here, you have to include H2O. And the reason you have to include H2O is because this base is not producing hydroxide. It's accepting a proton. And if you're accepting a proton, how can you accept a proton if you don't have another part of the chemical reaction, the H2O? And it'll always be H2O in this case. So the H2O donates the proton to our NH3+. If you have one of these compounds, in your simulation, that compound looks like this. It's just a B for base. You have to include H2O in your dissociation equation. Amphiprotic species, a couple of fancy terms for you. There are some compounds that can act both as an acid and a base. Amphi means both. Amphibians are both on land and water. So this would be a compound that can act as an acid or base. And don't worry about the gain or lose electrons. This is a definition of acid bases. That's beyond where we're going in chemistry right now. But an example of this would be H2O. The amphiprotic species up here, H2O in this case accepts the proton. And in this case, it donates the proton. So we have this compound that can act as a base up here, and it can act as an acid down here, donating the proton. So this would be amphiprotic. H2O can be a base or an acid, depending on the situation. Polyprotic means many, and that would be an acid that can donate more than one proton. Polyprotic species would be phosphoric acid, H3PO4, and you'll see in the first one, we call this the first dissociation equation. It's the first proton being removed from it, and we get this. And then this could also donate another proton, the second dissociation equation. And this particular acid could donate 3. We could do another dissociation and lose this proton. So if it can donate more than one proton, it's called a polyprotic species. If you look at a can of Coca-Cola or Pepsi, you will find this acid is in Coke or Pepsi, phosphoric acid. Take a look at it if you have any of those laying around. A couple practice problems. Let's see if you can write this. Formic acid is an acid that some ants will be able to spray out as a defensive mechanism. But this is what the compound looks like. There is a proton here, and it's this proton right here that gets donated. It's actually this one in the structure. What would that look like when it donates that proton? See if you can write that equation. What's the dissociation equation for this acid? Okay, hopefully you can write that equation. Here's our equation. All you want to do, if you want to include H2O, you don't have to include H2O, but if you want to include H2O, we just take our acid, and we know it's an acid. It just told it to us that we're an acid. And we take this proton, we donate it. And the donation would go to their H2O, so we get H3O plus. And then we just want to ask ourselves, what's left over after this proton's gone? Well, I get CHO2, and it has a -1 charge because we lost one positive proton. So that's how I get my chemical reaction here. What's my conjugate base for formic acid? Well, formic acid acts as an acid on this side. You want to ask yourself, where is the other part of the compound? Here it is on the peroxide. Well, this is my conjugate base of it. And that conjugate base, if we act in the reverse direction for this chemical reaction, this proton here would be donated back to my formic acid, and that's what makes it a base. So that's my conjugate base. Okay. Let's do another one, citric acid. If you've ever had a sports drink that tastes like a citrus fruit, they've added the citric acid in there to make it taste like that. How do I write this equation? See if you can write this dissociation equation for citric acid. Okay, here's your equation. I write out I didn't write my formula up here. This is formic. Whoops. I should have switched that. This is citric acid, our formula here for citric acid. But you'd write it out like this. We lose our one proton again. This gets donated to H2O. And the only thing that's left is C6H7O7 with a -1 charge. And my conjugate base of my citric acid, this is my acid on this side, the conjugate base would be right here. And that's the citrate ion. And if you look at any of see if you can find this, anything that is flavored around your house as a citrus, you'll find probably on your nutrition label citric acid added for that flavoring. Okay. So that's it for this week for new material. For your homework this week, you're doing an acid-base simulation. You're looking at some diagrams of what it looks like when an acid dissolves, what a base does when it dissolves, and then what's a strong acid and what's a weak acid. What's the difference between these two terms? And what's a strong base and what's a weak base, and what's the difference between these two terms? That's your goal at the end of the simulation. You should be able to describe this to someone who doesn't know anything about chemistry. What does it mean to be strong and weak? And you might even try to describe it to a sibling or to your parents. I hope you have a good week. Ask me questions if you have any, and I would be glad to help.